And because those are scattered in time, more or less randomly, this is a situation where we might anticipate that a Poisson model would work. The actual random variable is how many calls come in a randomly selected minute. So even though the average is 2.7, the actual observed values of the random variable, we could get 0 calls in the next minute, or 1, or 2, or 3. It's got to be a whole number. That's why this is a discrete random variable. It just takes these specific values. Okay? And then the question here is essentially what's the probability that the value in this next minute is going to be 5 calls. Okay? The calculator handles this really well. You just say Poisson PDF. PDF stands for probability distribution function. What's the probability in this Poisson distribution? You have to specify what the mean of the distribution is. So the syntax here is Poisson PDF mu. Have to specify the mean of the distribution. And then k, what's the specific value you're interested in. And if you plug that into your calculator, you get this, about 8%. It's very easy computationally. The thing that's hard is figuring out, okay, this is a Poisson situation, so I've got to pull up a Poisson PDF and remembering this syntax of what I need to put in the calculator. Let's see. Here's another random variable, x, and this is defined to be the number of times a gambler wins in 10 consecutive roulette bets on red. This is not the example we looked at before, where the random variable was how much money do you win or lose in a roulette bet on red. This one is saying, try that experiment 10 times. So we're going to do that bet on red 10 times and spin the wheel 10 times. And x is going to be the number of times the gambler wins. Okay, so what values can x take? If the gambler is really unlucky, x could be 0. 10 bets, 0 wins. If the gambler is really super lucky, maybe they could win 10. So any number of wins between 0 and 10, it's a discrete random variable with values 0 through 10. This is characteristic of a binomial probability distribution. Basically, a binomial probability distribution shows up anytime you have a fixed number of trials, and every trial has a fixed probability of success. In this case, n equals 10 is the number of trials. The probability of success, as we saw in the early examples, about 47%. So the probability the gambler will win exactly 6 times out of 10 is given by the calculator binomial PDF, probability distribution for a binomial random variable. You have to specify how many trials, the probability of success on each trial, and the number of successes that you're specifically interested in knowing the probability of. So the syntax here is binomial PDF and NPK. N, the number of trials, P, the probability of success, in this case of winning on this bet of red, and K, the specific number I want to know. One more example. So here's one with a normal distribution. Heights of U.S. women. We had the example of men. U.S. women, the mean is about 64 with a standard deviation of 3 inches. This notation is used in the book. Capital N means you've got a normal distribution, and then you have to specify to understand what a normal distribution is, which specific one it is. You need to know the mean and the standard deviation. So this gives this as the mean is 64 inches and the standard deviation is 3 inches. So what's the probability that a randomly chosen woman will be 5'2" to the nearest inch? Okay. Here we use normal CDF. It's not probability distribution, it's cumulative distribution function. And you want to choose a CDF anytime you're trying to find the probability of a range of values, not just one specific value, but a whole range. And for these continuous probability distribution, that's always going to be the case. Let me draw a picture of this model. Basically, women's heights have this symmetric bell-shaped probability distribution with a center at 64 inches, 5'2", 5'4", and a standard deviation of 3 inches. You know, so one standard deviation would be this way, one standard deviation would be this way. I don't need to put a lot of detail in there. And we're looking for the probability of selecting a random woman and having her be 5'2". So basically, here's 62 inches. Let me redo my axis here. But really by 62 inches, I mean, what's the probability that height is going to fall somewhere between 61.5 and 62.5? Between 61.5 and 62.5. And I'm asking the calculator to help me find that area, where the area under the entire curve is 100%, okay? So I want a cumulative distribution function. I want to say what's normal CDF, and then I want to go from the lowest end of the scale to the highest end, 62.5. I want to go from the low end of the range to the high end of the range, and this is in a distribution with a mean of 64 and a standard deviation of 3. Get the other side, and you get 10.6%. One more question thrown in here. What percent of U.S. women are shorter than 5 feet? Okay, that picture would look sort of like this. Saying how much area underneath this curve falls below 60 inches. Well, in theory, this curve continues forever, but you know from the rule about 3 standard deviations that 97.3% of all the observations fall within 3 standard deviations. That would be 64 inches plus or minus 9 inches in this case. So this gets very, very thin. But in effect, you're asking the calculator, how do you find me the area, cumulative distribution function, between negative infinity and 60 for a distribution with a mean of 64 and a standard deviation of 3. And the problem is, how do you enter negative infinity? Here's my favorite rule of thumb for that. Approximate negative infinity with the mean minus 10 standard deviations. Almost all the observations fall within 3 standard deviations. If you go plus or minus 10 standard deviations away from the mean, there's really effectively no chance that you're going to be farther away than that. The calculator will return a probability of 0 above or below 10 standard deviations away from the mean. So I just took my 64 inches, my mean, and 10 times 3 is 30. 64 minus 30 is 34. That's a good approximation for negative infinity. Just find me the probability that a randomly selected female will be between 34 inches tall, shorter than 3 feet, and 60 inches, and that's going to be the probability that she's under 5 feet tall. That turns out to be 9.1%. Enough.